So our last talk is going to be Peter Thiemann. He's going to be presenting this really elegant approach for specifying session types that has the added benefit of producing some performance benefits during type checking. So, good one.
Thank you. Thank you for the introduction, although I don't. All right. Let me take you on some programming task. Namely, I would like to send some data over the network, and in my case, the data is taken from this algebraic data type of simple arithmetic expressions. Something that you might come on to to solve this task is a types discipline called session types, which allows you to do bidirectional type-safe communication between, in this case, two partners. And let me just show you an implementation of that. So here we are defining some function. It takes a value of our expression data type. Then it takes a communication channel, which has a session type, which I'm going to explain in a minute. And then it returns the communication channel after the expression has been transmitted on it. And the way that this code is constructed is quite natural. You would match on the expression. If it's a constant, well, then you grab the communication channel and you issue a command which is called select, and it says, okay, select the constant alternative of the protocol, and then on the same channel you send the payload of the constructor, which is the number I. If you matched on the other kind, add of two sub-expressions, well, then again you issue the select command and switch the protocol to add, and then that allows you to send two expressions corresponding to the two sub-expressions that we've seen. The corresponding session type is the nice recursive type you see down here. So this internal choice operator tells you that you as the sender here has a choice between two commands, constant or add, and then if you choose constant, then you have to send an integer. Otherwise, if you choose add, well, then you have to execute the protocol recursively 2 times in a row. So this semicolon operator is sequencing, and right there, let's have a closer look at this kind of type. So this type is not a traditional session type, if you are a little bit familiar with the literature. So this is called a context-free session type, and that has 2 properties. The first property is that recursive types are really equal to their unfolding, so you have an equi-recursive interpretation of that. And the second specialty is that recursion variables may occur everywhere, anywhere in the type. Yeah, so in particular, you can have here a recursive call and then another recursive call to the same thing. In the traditional style session type, that's not possible. You can only have tail recursion, so this first X wouldn't work. All right, looks like the problem is solved, right? Why am I here? So the catch is there. Even though there is a nice type system for these context-free session types, it turns out that type equivalence for these guys is a pretty difficult problem. It's doubly exponential in theory. It turns out this is not just a theoretical thing, but the practical performance is also quite hard to predict. If you look here on the left on this scatter plot, on the x-axis, you see the sizes of types, and on the y-axis, it's in logarithmic scale, by the way. You see the timing in milliseconds. You see that the timing for just a simple query is t equal to t, ranges from, that was milliseconds, so that would be 100 microsecond up to 100 or hundreds of seconds, because up here the line is timeouts. So there's a problem. Question, and that's what puts our work here on the table, can we somehow make type equivalence linear and even add expressivity? Not lose something, but add something. Right, indeed, you can do that. And if you don't remember anything else from the talk, please remember this slide here. What we're going to do is we're going to take the well-known recipe of algebraic data types, namely to combine the naming of the type with recursion and then having a nice sum of product construction below, and apply that whole methodology to session types, giving algebraic session types. Namely here you also have naming and recursion combined, and then instead of sum, you have choice, and instead of product, you have sequence. That means recursion now works via nominal type, and that means type equivalence is linear in the size of types. Moreover, we have a new form of parameterization that, in connection with polymorphism, gives way to pretty exciting modularity possibilities for constructing session-typed programs. Let me now take you through this construction in 3 steps. So step 1 is the following. If you have an algebraic data type definition, then you can actually, you just need to squint and see this as a protocol by just interpreting the data constructors as selector tags, as the names of the commands that switch around the protocol. Now, as an example, here we go back to this expression data type. These are the types of the constructors. And now what we're going to do is we're going to interpret these constructors as commands for where we used select before. So if we're sending, then select of const, just derived from this definition here, this is going to turn a channel that is ready to send an expression on it, and then something, into, well, we know it's a constant, we switch to constant, so the only thing we need to do now is send an integer, the payload of the original constructor here. And miraculously, the same also works for add. So if we have a channel that's ready to, where we can send a single expression, and now we know it's an addition, an add expression, well, then we need to send 2 sub-expressions, so that is going to be the type of select of add. If we go to the receiving end, well, things just swap around in a dual way. So a question mark expression, that's a channel that's ready to receive an expression. On that, we can apply the case operator, so that receives a command and deciphers it. If we get a const, well, then all that remains to do is to receive the payload, the integer. If we receive an add, well, we know we have to receive 2 more expressions from that. And just for your convenience, I'm showing you the send expression function again, and you see, I guess you remember, the code actually didn't change. So the only thing that changed was the type up here. So only the session type changed. Before we had this s-expr, that was this recursive type that we discussed in detail, semicolon s, and that just changed to the protocol type receive an expression and then s. Notice that this sequential composition operator, which has interesting properties, it's associative, so there's a monoidal construction there, this operator is no longer required. And that's one of the culprits for the inefficiencies in type equivalence, and it also causes some complications in the meta theory. So we are very happy to be able to get rid of that without losing anything. Step 2, protocols that only go in one direction, as the one I showed you, are pretty boring. So we'd better be able to also add directionality, that we can send methods forth and back. So what we do is we move from data specifications to protocol specifications that add directions, essentially, to the arguments of a data type declaration. Now that also changes the perspective. Now a data type, a protocol type, it's classifying just behaviors. So there are no runtime values associated to such a type anymore. But apart from that, the mechanics I showed you before for the constructors of the data type, of the algebraic data type, work just as well. So here we have a protocol simple arithmetic. I could have called it unary operator. We need a tag here, and then it says, well, there is an integer traveling in one direction, and then the second part of the protocol, there's an integer traveling in the opposite direction. And notice this definition here, this protocol definition doesn't yet fix what is sending. Doesn't yet fix what's sending and what's receiving. To fix that, we actually need to use it in the context of selection or in a case. If we get it into a sending context, well, then send a simple arithmetic expression. We only have the command neg here. Then it says send an integer and receive an integer. If we use it in the receiving context, well, things just flip around. Okay. Here, so this just to show you some code here. This is a server that makes use of this protocol. So this is the simple arithmetic protocol in receiving direction. So we case on the channel, and then we first receive, and then we send. So all that is type checked, and that is fine. So well, just to give you an idea, I don't want to go in detail through the code, but you can do that on your own pace in the proceedings. Right. Why did I show you that? Well, to have a nice example for the next step where we add parameters to protocol. So a protocol definition can also abstract, and the abstraction is now not just over data types, but you can also abstract over whole protocol types, like the simple arith thing that I just showed you. And this is a kind of parameterization that's original to our work, and it's just not possible to do that in earlier work. So here's a very simple parametric protocol. It's called repeat X because it behaves like a list data structure. Only what you're repeating is not some data value, but you're repeating a protocol. So we have got two constructors, quit to stop, more for more of this protocol, and then now this X here says, or plus X says, execute the X protocol, whatever it is, in forward direction, and then continue with repeat of X. So do it again. And the remaining mechanics is as before. So select just distributes the sending instruction on the arguments of the constructor here. Notice now here we have sent some P, and right now we don't know what P is. So the selection of more is polymorphic in the protocol, and we can use it at any instance. And for branching, it's just the same. It's just again flipping the, well, going to the dual essentially, flipping from sending to receiving. So what can we do with that? Well, now we can actually parameterize over a whole server for a protocol. So if we consider this type here, this was the type of the simple arithmetic server. So now we can write a repeater that takes a value of this type, and then it returns, well, a server that repeatedly executes the simple arithmetic protocol. Now, the code is not very interesting, so we're just exercising the repeat protocol. Either on this channel I'm receiving a quit, well, done, or we're receiving more, in which case I'm first invoking the simple arithmetic server, and then I continue. And this typing here is nice, so I can just apply the repeater to the simple arith that I showed you before. I just showed it to you for that purpose, and there you go. Notice now here in the definition of repeater, there is nothing that forces me to use it with only simple arithmetic. And because I can also parameterize over protocols, let's just do that. Go from server for arithmetic, repeater for arithmetic, to repeater of anything. So that gives rise to a nice type synonym. Service over P is just for all continuation sessions, receive some P and S to S. So that's the function, that's the definition of a service function that services the protocol P. And now the repeater, with this synonym, the repeater gets a nice type, namely service of P to service of repeat P. Implementation, as on the previous slide, and also the use is just as we saw it before. Right. Well, now getting to the rest that you can find in the paper. So we have a full implementation of that system with some practical extensions. You can download that as an artifact, or you can have a look at our repository. So the implementation consists of a type checker and an interpreter, and it's implemented in Haskell, and I'm welcoming you to play with that. Another reason for the implementation is, well, we used it to benchmark the type checker. So I complained before about the theoretical time complexity of type equivalence. So for context-free expressions, it's doubly exponential in the worst case. And for asymptotic session types, for algebraic session types, we are proving in the paper that the type equivalence is asymptotically linear in the size of the type. Question is, of course, does it make a difference in practice? Since I'm down to 1 minute, I'd love to talk about this. Ask me in the questions part. What else do we have? What else is in the paper? So the paper has a type system as an extension of most linear system F with algebraic session types. There's a kind system that distinguishes between sessions and protocols. Remember, they classify behaviors, not values, and general types. So everything is built on a bidirectional algorithmic type system. Then there's the usual things, LTS-based small step operational semantics and proof of type soundness. And that leads me to the conclusions. I've introduced you to algebraic session types. So that's based on transferring the construction principles of algebraic data types to session types. We believe it's an elegant approach to working with regular and context-free protocols because it frees the programmer from writing complicated recursive types with mu operators and all that, and instead they can reuse knowledge that they've gained by using algebraic data types. Moreover, I've shown you that there's a nice way of modularly constructing protocols because of these new ways to parameterize. We've got efficient type checking, also thanks to the nominal types, and there are further extensions possible by, well, just being inspired by work that has been done for algebraic data types. Well, thank you for your attention and questions.
As always, people can come to the microphone to ask questions. I'll kick us off with perhaps you could tell us a little more about sort of the practical benefits of this. The practical benefits.
Do you want to see the slides?
Yeah.
Do you want to see it? Or do you first want to ask?
Answer the first question first.
Go for it. Oh, yeah, answer my question first.
Okay. It's really very hard to understand what you're saying on the mics up here. So that's right. Right. So this scatter plot now has blue dots for the timings of our implementation of algebraic session types, and the red dots are the one that you saw in the beginning. So what did we do here? We randomly generated algebraic session types of different sizes. Then we translated those to context-free session types. So we used an implementation that's called FreeST, which is done by my co-authors. And again, we're reporting timings for the question, is t equal to t? And as you can see here, so still logarithmic scale. So the blue stuff is always down here, and that should be around, well, everything is less than 100 microseconds. And up here, I told you before, so this is a bit unpredictable how the type checker for context-free session type behaves, but there are lots of instances for larger types where it just times out after 100 seconds. Well, thank you for that question.
So one interesting kind of server is one which spawns a new process to deal with each request, so that the client would then continue communicating with that newly spawned process. Does your idea support this? And if so, does it cause any extra complications?
Okay, so as far as I understood your question, does our methodology also support forking expressions and communicating with them?
Well, so you would need to include a new channel in the message that you send back to the...
You mean higher order? Yes, yeah, we support sending, yes, we support sending channels over channels, yes.
Hi, nice talk. So you said that the algebraic session types are more expressive. Is there actually a function that translates the context-free types into the algebraic types?
Okay, that's a good question. That's something that we've been working on. We believe it's true. We don't really have a formal proof for that. We are currently working on the formal proof for the simpler case. So we are very confident, that's probably the right thing, that we can translate every traditional session type program into this setting. We are also confident, but we have a construction, but we don't have any kind of proof so far. We are also confident that we can translate most context-free session types into this setting. I don't think that it will be possible for all of them, but I think the system is so much simpler to use and so much more efficient that it's okay to lose a little bit.
So actually, let's take this one offline because we're running a little bit behind. So let's thank Peter and the rest of our speakers again. And let's also thank the student volunteers and the AV experts who've been running the session for their hard work. So as a quick recap, we have a 10-minute coffee break. So go drink your coffee, and the next session will resume at 4 o'clock in this room in Canary, Cyprus.